looks like this so we can put it into a series. Questions about that? Okay, no questions? So here's the goal for today. The goal for today is, what if you have a function, maybe sine x? No matter what I do to sine x, I can't make it look like this. I can't integrate it, differentiate it to make it look like this. There's just no way. Right? So far, it only worked if we could make them look like this fraction here and turn it into a series. So the goal for today is, hey, what if you have another series and you want to know how to turn, another function and you want to turn it into a series? And so the first one we're going to talk about is called the Taylor series. So we're going to go through how to find a series for any function. For any function. So there's a couple assumptions we have to make. I'm on page 155, by the way, if you're not there. We're going to assume that every function can be written as a series. Remember, this is the way we said that we're going to write series in general. There's a different constant for each term, and it could be centered at a. This one is centered at x equals a. And so it would look something like some c0 plus c1 times x minus a to the 1, c2 x minus a squared. So it's the same notation we've been talking about. We're going to assume there is a power series for that function. We also have to assume that all the derivatives exist. And what I mean by that is the first derivative, the second derivative, the third derivative. You can find all the derivatives. If the derivative was undefined, this wouldn't work. But if you can find all the derivatives, then you can turn it into a power series. And so our goal is to find all the coefficients for every function. So if it's sine x, maybe this first one's a 7, and that one's a 3, and that one's a 9, or something else. And if it's cosine, maybe those are different constants. But that's the goal, is to find the constants so you can find the series for every single function. Everyone okay on the goal? All right, so before we go on, I have a little, okay, so what are the coefficients? That's what we want to find. My question for you is, what's f of a? If I plug a into this function, that's the same as plugging a in here for all my x's. What will I get?
0.
C0, right? I'll get C0 plus this term will be 0, that term will be 0, that term will be 0. It'll just be C0. Okay, so look, I already found one coefficient already. The first coefficient is what you get when you plug a into your function. So if it's centered at 4, I'm going to plug 4 into my function, and that'll be my first constant. Everyone okay what I mean by that? Got one of them. Now we have an infinite more to show. So the next thing I want to do is start taking derivatives. I have it written out in your paper, but I like to write them down so it makes sense. And I'm only going to take the derivative of this portion. And this portion technically is the same. But if I take the derivative, that C0, what's the derivative of C0?
0.
0, because that's a constant, right? So this is gone. Plus, oops, plus, 0 plus. So what's the derivative of the next term? Just C1, right? Because derivative of x is just 1. And then we're going to start using the chain rule. To take the derivative of this one, I'm going to bring down the 2, x minus a to the 1. You guys see what I'm doing there with the chain rule? Derivative of the next one, bring down the 3. So that's 3c3, and subtract 1 from my exponent. Let me add one more just for fun. What's the next one going to be, even though I don't have it up there?
4c.
4c4, x minus a to the third, and that keeps going. What's f prime of a? What happens when I plug a into my first derivative? I just get c1, right? Because all of these become 0 again. 0, 0, 0, 0, 0. So look at it, I got 2 constants now. Almost done. Infinite more to go. Everybody okay there? And I have these derivatives written down on your paper. So if we take the second derivative, again, that goes to 0. The derivative of this guy is 2c2. I hope I didn't multiply that. Okay, good. I'm going to very specifically not combine these. So when you take the derivative here, I know most of you would just say, oh, that's 6c3. But I'm going to make sure to leave it written out as 3 times 2, just so I can make my point in a little bit. You guys all right with that? 3 times 2 times c3, x minus a to the 1. And this one is 4 times 3, because I'm bringing that 3 down. If we simplify, we won't see it as well. X minus a squared. Bless you. And that keeps going. Guess what I'm going to ask you next?
Yeah. Prime of it.
Yeah, f double prime of a? What's the second derivative evaluated at a?
C2.
C2?
2C2.
2c2. I didn't hear the 2. Right, because all of these will be 0. 0, 0, all those will be 0. But this one will be what's left. Better do another derivative. Third derivative. This goes away. This will be 3 times 2 times c3. I'm going to pause for a moment. When you're working through these problems later, I highly recommend not simplifying, like I'm doing here, until you're done taking derivatives and evaluating, because patterns are harder to see if you've simplified than if you don't. So just kind of leave it like that for now. So that's a derivative of this guy. What's the derivative of that guy? This one, what's going to happen? 4 times 3 times 2, c4, x minus a to the 1. It'll keep going. What's the third derivative evaluated at a?
2 times 3 times C3.
3 times 2 times c3. Now, I didn't take the fourth derivative here, but let's just see if we can figure out what it is. This is how we write the fourth derivative. What do you think is going to happen when I do the fourth derivative and I want to plug in a?
4 times 3.
I'll be left with this coefficient, right? Each coefficient just keeps moving over. Ah, someone just said factorials. We were just talking about those too, Zach. 4 times 3 times 2, c4. So Chad sees that these are factorials. Okay, the ones are missing, but when multiplied by 1 doesn't change anything. Let me squeeze them in there to point that out. Technically, this is a 4 times 3 times 2 times 1, right? There's a times 1 in there. And this is 3 times 2 times 1 times c3. And this is a 2 times 1. And this is a 1. There's a 1 here. So this actually has to go back and make sure you understand factorials. We were just having a conversation in the lab about how some people never saw factorials before Math 16. So most of us know, for example, that 4 factorial means 4 times 3 times 2 times 1. And 1 factorial is just 1. What do you think 0 factorial is? It's actually equal to 1. It's defined to be 1. And the best explanation I can give you that's short and sweet is it's similar to when you have exponents of 0 and you get a 1. It's similar to that when you go to reduce things. But by definition, they define it to be equal to 1, even though you're thinking, wait, you're multiplying by 0. But technically you're not, because you're supposed to go down to 1 and you're already past it. So this one has its own little special rule. So the reason I wanted to point that out is notice what we have here. This is 4 factorial. This is 3 factorial. This is 2 factorial, 1 factorial, and this is actually 0 factorial. See that there? Each one of these has a factorial in front of it. Factorial notes as we go. Okay, where did I leave off? Did I write it down? I did. Okay, so we're going to read it off to the side. I'm going to erase my for example over here. So for example, let's just talk about the fourth one. Well, the third one's prettier. The third derivative at a is equal to 3 factorial c3. You guys agree with that? Can you solve that for c3? What is C3 equal to?
First, 3.
The third derivative evaluated at A divided by 3 factorial. Right, just dividing both sides by 3 factorial. What do you think C4 equals?
Fourth derivative divided by 4.
The fourth derivative evaluated at A divided by 4 factorial. So let me get this straight. I want to point this out. We know how to find the fourth one. We know how to find the third one. We could do the same thing with the second, the first, and the zeroth. The zeroth one. That's an English word, I'm sure. In general, how do I find the nth coefficient? I'm going to end up dividing by n factorial. What did you say, Joseph?
Oh, so we take the limit.
We're not taking a limit. I'm just talking about, for example, if I say I want the 75th constant. Well, we know the fourth constant needed the fourth derivative and a 4 factorial. And we know the third one needs the third derivative and 3 factorial. So if I happen to want the 75th constant, I would take the 75th derivative. So it's not a limit. I'm just talking about a specific one. The 75th one divided by 75 factorial. So if it's the nth one, the way we write it is, we're taking the nth derivative, evaluated at A, and dividing by n factorial. So you should have that squeezed off maybe somewhere to the right, about 2/3 down your page there, right before or next where it says Taylor series. This right here is our best friend. This is telling us how to find the coefficient for every single term of your series. The problem is, I don't want to take the 75th derivative of a function. That's a lot of derivatives. And what about when I get to the 175,000th term? I don't want to take that many derivatives. So what we're going to do is take some derivatives and look for a pattern. Look for a pattern of derivatives. Pause for a moment before I point out what we've got in our notes next. Questions on notation, what I've been doing, what it means. No questions? All right. So my next line down actually defines what a Taylor series is. So this guy Taylor figured out how to do this, which is pretty genius if you ask me. And he says that for any function, you can write it as a series, n equals 0 to infinity, of the nth derivative evaluated at A over n factorial times x minus a to the n. How does that compare to where I started over here? How does that formula compare to this formula?
Cn is equal to the function of n over n factorial.
Yeah, we just replaced Cn with what we just figured out that Cn equaled. We figured out what the pattern was, how to find each constant. So instead of writing out what each Cn is, he just sticks them in there. Here's my Cn. This part right here is Cn, meaning the nth constant, the first constant, second constant, so forth. And I think it actually helps to write out what that means, which I have on your paper, and now you can copy it. The first one is f of a, because when I plug 0 in there, the 0th derivative, there is no derivative, that's just your function evaluated at a. Right, the 0th derivative means you haven't taken any derivative. Now, I'm going to actually add something that's not on your notes, so I'm going to put another color so that you see it. Over 0 factorial times x minus a to the 0. That's just your first term. Why didn't I put the red part on your notes?
Because it cancels out?
Yeah, it cancels out. 0 factorial equals 1, and anything to the 0 power equals 1, which is why that red part wasn't written in your notes, but I think it's important to know it was there. It just got simplified in your notes. Then the next term is the first derivative evaluated at a. Again, I didn't write the next part. over 1 factorial. Right, that's what this tells us. Just start with 0, do the first, 0th derivative, then the first derivative, then the second, and so forth. Times x minus a to the 1. 1's not written there either on your notes. You see why that red part got left off? It just got simplified. When you get to the next one, it gets a little bit clearer because nothing's missing then. The next one will be the second derivative evaluated a divided by 2 factorial x minus a squared. I think in your notes, I better put that in red. Factorial's not there either, is it? In your notes?
It is there.
Oh, it is? Oh darn. Good. I'm glad I put it in there. Technically 2 factorial is just 2, so I'm surprised I didn't simplify that one too. But each one, notice this fraction, the denominator of this fraction, this factorial down here always matches this exponent on x minus a. The 0th derivative, 0 factorial, 0 exponent. First derivative, 1 down here, 1 exponent. Second derivative, 2 down there, 2 exponent. And so forth. So this is how we're going to turn any function into a series. We're going to just take a bunch of derivatives and hope we find a pattern so we don't have to write out every single term. There's some that are so messy that we only can write out the first few terms because the pattern is really hard to see. We'll see some of those coming up. So that's defined to be a Taylor series. That's a Taylor series. And then a Maclaurin series, right underneath there is a special case. Maclaurin is a Taylor series, but the center is at 0. It's a Taylor with a equals 0. So Maclaurin just, made everything simple. He says, forget all this x minus a stuff. Let's just plug 0 in for a. Make the center 0, it's a little bit nicer. So for Maclaurin, all my a's become zeros. So I have the nth derivative at 0. I still have the n factorial. But if a equals 0 here, x minus 0 is just x to the n. Just look prettier. Center at 0. Makes everything look nicer. See how it's the same thing? I'm just replacing all my a's with zeros. It'd be the same thing though. It would be f of 0 over 0 factorial x to the 0. Again, I simplified that first one. This part should have been in red. That part simplifies to 1 over 1 again. And then the first derivative at 0, 1 factorial x to the 1. Again, notice in your notes, that part's already simplified. And then we keep going. Second derivative at 0, 2 factorial x squared. Yes?
I would still have the series in front of the
Ah.
function. The summation
here.
in 0.
Thank you. Summation notation is missing. Thank you, Nick. The series. Thank you, Nick. I missed that. Good catch. What earns the big bucks. So it seems all kind of obscure and weird, but it's actually really helpful if you can follow the pattern, and I can't stress enough that any term, your derivative, your factorial, and your exponent are always the same. You're taking the second derivative, it's a 2 factorial, it's exponent of 2. When I get out to the 75th one, it's going to be the 75th derivative and a 75 factorial, an exponent of 75. Questions? I think an example will probably bring up some questions.
Yeah.
How to use it. Okay. So let's look, I think I have my first example coming up. It says find the Maclaurin series for e to the x. I'm going to start over here. I want to find the Maclaurin series for e to the x. So find the Maclaurin series means find your derivatives, find all your coefficients, write it as a series. There's no way I can write e to the x as a 1 over 1 minus something like we did in the previous section, right? There's just no way. But what we're going to do is start taking some derivatives so we can follow this pattern. So step 1 is always just take a bunch of derivatives until you start seeing the pattern in your derivatives. So I'm going to start them over here on the side. My original function is e to the x. What's my first derivative? E to the x. What's my second derivative? E to the x. This one is so easy it's quite boring. All my derivatives are going to be e to the x. Right? Every derivative. Even when I get to the nth derivative. The 75th one, which is my favorite one today for some reason. When I get to the 75th derivative, it's going to be e to the x. Okay, great. So knowing that, I think I can write the series. So f of x equals e to the x. That's going to be a series starting with n equals 0 to infinity of, now I'm going to write each term out. I'm going to write the generic one first, excuse me. I'm going to write this first. What's fn? The nth derivative is e to the x, but we're evaluating it at 0. So it'll be e to the 0. I'm going to actually write that in here right now. E to the 0 over n factorial times x to the n. Are you talking to me or to you, Joseph?
Myself.
Okay. Can I help you with your
I'm
conversation?
just thinking, wouldn't the Maclaurin series with this one, in case, make it easier comparison to that one?
Oh, yes. Maclaurin series are always nicer than the Taylor.
Yeah, that's all.
Because plugging 0 into functions makes them come out usually much nicer than plugging in 73 or
This
whatever.
looks like it'd be a lot
Uh-huh.
easier.
Mhm. You're right. You're right, it does. Questions on what I wrote there? Technically, we're almost done. Would anything here simplify? E to the 0 is just 1. So this series is 1 over n factorial x to the n. We're done. This is the series for e to the x. We turned e to the x into a Maclaurin series. Most of your Taylor and Maclaurin series will have factorials in them. Some of them will reduce out, but this one definitely has some factorials in it. If I asked you to write out the first 4 terms, just to make sure you know what we found here. What do I do to find the first 4 terms?
Zero.
Yeah, plug in 0 for n, that's going to be my first term, right? So if I plug 0 in here, I'm going to write that out. E to the x equals 1 over 0 factorial x to the 0. And I plug 0 in for the first term. Now I'm going to plug 1 in. 1 over 1 factorial x squared. Oops, x to the 1. I can do that. I just made that point to you guys. Make sure that exponent and that factorial match. Plus 1 over 2 factorial x squared. How many did I ask for? Did I ask for 3 or 4? I asked for 4? Okay. I can't remember what I asked for. 3 factorial x cubed. And we could keep going if we wanted to. So if you were doing this problem on, say, your website, and it said list the first 4 terms, you would actually simplify each of these. knowing that 0 factorial equals 1, your first term is just 1 over 1, x to the 0 is 1, it's just 1. Plus 1x plus
X squared over 2 factorial.
x squared over 2 factorial, but 2 factorial is just 2, 2 times 1, right? 1/2 x squared. It's not wrong the way you said it, by the way, but we almost always just put the coefficient out in front. And what's 3 factorial? 6 x cubed. So those are the first 4 terms. Simplified. So what we've actually have done here blows my mind. We've taken the e to the x function and turned it into a never-ending polynomial. Again, this is what calculators, excuse me, and computers do to actually evaluate these things. It turns them into series. It does so many terms. And then if we really wanted to for fun, we could find the interval and radius of convergence. But in the interest of time today, we're not going to do that again because we're a little tired of that after doing it in the last couple sections. But it does have an interval and radius of convergence. Questions? We're all right there? Okay. Let's find the Maclaurin series for sine x since I brought it up earlier. Let's take a trig function, turn it into a polynomial. That's what we're looking to do. Before I go on, anybody change their mind about questions? No? Okay, I'm going to erase all this because we've got the formulas over there. Sine x is a little bit different.
It's like an alternating series.
I couldn't hear you.
I said it's like an alternating series.
Yeah, because sine is sometimes positive and negative, it will end up being an alternating series, like an alternating series. I like that even better. F of x equals sine x. Same directions, we want to find the Maclaurin series. Oh, this one did ask for radius of convergence. I'll have to go back and do it. I didn't see I asked for that. That's okay, we'll do this one first. Maclaurin series. So what do you think I should do?
First one.
Take the first derivative, which is cosine x. Take the second derivative, which is negative sine x. Take the third derivative, negative cosine x. He's giving me hand signals back there. Now it's going to start repeating because the fourth derivative, the derivative of negative cosine is negative sine. So I'm back to sine again. And then they'll just start repeating. I'm going to write out a few more just to make that point. The fifth derivative will be cosine x. Sixth derivative will be negative sine x. These are a little bit tedious. I hear your sighing already. Oh, was it young? I'm boring you, see? I'm boring this. Lack of oxygen? I'll open the windows. Oh wait, we don't have any. If we had windows, I'd open them. So I took a bunch of derivatives. This one's a little bit more complicated than this e to the x example because here we could just say, oh, here's a formula for the general derivative. Can I do that over here? And just write a formula for what the general derivative is? Like the 75th, that's been my one for the day. If I wanted the 75th derivative, do we know what it's going to be? No, we know it's going to be one of those 4 options, right? But we don't know for sure. We could probably figure it out, but this is a case where you just don't have a general formula for the derivative. So we're going to actually have to start out writing some terms to look for the patterns here. So I took a bunch of derivatives. What else do I need? What am I plugging into those derivatives if I'm doing a Maclaurin series?
0.
I'm plugging 0 in. So let's plug 0 into all these. Oh, no, lose my word Maclaurin here. What's f of 0? Sine of 0? 0. What's f prime of 0? 1, because cosine of 0 equals 1. What's f double prime of 0? 0. You guys see that because sine of 0 equals 0, every other one is going to equal 0? You see that? I'm going to put all those in there right now, save myself some time. Everything that has a sign in it is going to be 0. Oops, it's not a double prime, it's a 4. The fourth derivative, the sixth derivative, all of the even derivatives turn out to be 0. But what happened to those odd ones?
It's between 1 and -1.
Say it louder for me, Joseph.
I said it's alternating between 1 and -1.
It's alternating between 1 and -1, right? Because negative cosine of 0 is going to be a -1. And then when we get back here to cosine of 0, that's going to be a +1. This one's going to be a -1. Same reasoning. So it actually is an alternating series once we start writing it out. So I took a bunch of derivatives, and the question I always get is, how many derivatives do I have to take, Jill? I don't know. As many as you need to till you can see the pattern. If you only did 3 of them, it maybe wouldn't have shown you much of a pattern. Right? So I like to do enough where you can start seeing what's happening. So let's just start writing out the terms. Let's not write out the generic notation. Let's just write out the first term, the second term, the third term, similar to what I did right here. Let's just start writing out the terms and see what happens. So what am I going to start with? What do I start with?
Is it sine of 0 over 0
Yeah.
factorial?
The function evaluated at 0 over 0 factorial x to the 0. And this is this f0 is the 0. This is the 0th derivative. I mean, if you wanted to, you could kind of think of it like as a 0 in here. Right? The function by itself is the 0th derivative because you haven't taken a derivative yet. So we're going to start with this number. So this is when n equals 0. This is when n equals 1, 2, 3, so forth. We're going to take all those numbers. So the first one was 0 over 0 factorial x to the 0. Plus, the next one, the derivative is 1. So these derivatives here are the things that go in your numerators. Right? The derivatives of what we found over there are what goes in each numerator. So the next one is 1 over 1 factorial x to the 1. The next one for the second derivative is 0 again, divided by
2 factorial.
2 factorial, because we're on the second derivative now, x squared. The next one is -1 over 3 factorial x cubed. I did this one, I got the first 4 of them done here. I might write out just a couple more. You don't have to do all of them, I'm going to write a couple more for me to figure out what happens in this series once we simplify it. Are there any questions on where I'm getting these numbers? Is everyone clear that these numbers here, these derivatives, are these coefficients, these numerators? 0, 1, 0, -1, so the next one will be 0. I've got 4 factorial x to the 4th. The next one will be back at +1 over 5 factorial x to the 5th. So what happens in this series? When I go to simplify this,
All the even terms are gone.
all these even ones are gone. This is equal to 0. This is equal to 0. That one's equal to 0. The next one's equal to 0. So when you have terms that equal 0, just throw them out. They're not part of your series. We don't need them. So now I'm going to rewrite this with just my terms I have left. We got this. I have 1 over 1 factorial x to the 1 plus negative 1 over 3 factorial x cubed plus positive 1 over 5 factorial x to the 5th. Just taking out the ones that I have left. What's the next one going to be?
1 over 7 factorial.
So I heard 1 over 7 factorial.
Let's say minus.
Negative 1. Okay, good. Just want to make sure.
So if we wrote, compared to writing just like one, plus negative 1 over 3.
You could have written minus in the front. That's fine. Yes. Did you ever understand his question? You could have written minus instead of plus and negative. And that keeps going. So you only end up with odd numbers, and you've got alternating series, right? That goes from positive to negative, positive to negative. So the goal is to take this now and write it in series notation, summation notation. And here's where it gets tricky. Oops. Well, I guess I could start at 1. Do we start at 0? Do we start at 1? What are we going to do? Well, how do we count by 2s? There's a variety of different ways to do this. So these are all odd numbers, all of them. Can I just put an n in there? Is n always odd? No. How do you know when you have an even number? Like, what can you do to recognize an even number? N times what will make it even?
2.
Right, 2n is even, right? No matter what. So guess what I have to do to turn an even number into an odd number?
-1.
Either subtract 1 or add 1, right? Just move over 1 either way. I'm actually going to do a plus 1. Subtracting 1 wouldn't be wrong either. 2n plus 1 would be odd, right? Because if I plug 0 in there, I'll get 1. What happens when I plug 1 in there? I get 3. And when I plug 2 in there, I get 5, and so forth. So very often we're going to use these expressions for things that are even or odd. You also could have done this. This also would have been odd. The problem with this is if I start at 0, I won't get 1, I'll get negative 1. So you kind of have to play around with it to make it match your series, but this sometimes works. But we all agree that this gives me each of the terms that I want. So how am I going to write that? Let's just talk about my denominators first. My denominators. I've got 1, 3, they all have factorials. I need something factorial. I've got 1, 3, 5, 7, so what am I going to put in there? 2n plus 1, right? That's what we just talked about. That's going to force it to be odd. 2n plus 1. If you're not sure, plug in 0, plug in 1, plug in 2, make sure you get those same terms. So that takes care of the denominator. We all right there? Bless you. X raised to what power?
2n plus 1.
2n plus 1. Remember this number down here, this factorial always matches the exponent. So if we've got a 2n plus 1 down here, we've got a 2n plus 1 exponent. And what's the only thing that I have left to worry about? The top, which is either a 1 or a negative 1. So that means it's negative 1 to some power. I'm going to put a question mark here for the moment. I need to force it to come out the right way so that it alternates.
Just n.
Just n. Because if I put just n there, when I plug 0 in there, negative 1 to the 0 is positive 1. When I plug 1 in there, negative 1 to the 1 is negative. When it's 2, it'll be positive. So what happens is even though these terms came from a different series up here. Like, for example, this was the 1, 2, 3, 4, this was the 6th term up here. It's now only the 3rd term down here, right? So forget that it was the 6th term to begin with. We're just looking at changing this one into this notation. And I claim that this works. And we'll give you all of those terms for sine. I've got the alternating, I've got the denominators with the factorial, and I've got the exponents with the matching numbers to those factorials. We've turned it into a power series. A Maclaurin series, to be exact. Questions? It's a lot of work. It's organizing your derivatives, it's evaluating all your derivatives, and then it's very carefully plugging into the formula, knowing that it's always the derivative over the whichever term you're looking at, factorial, and that same exponent. Zeroth derivative, first derivative, second derivative, so forth. Is that your hand I see, Zach?
Is it just coincidence that that is the power series for inverse tan?
It shouldn't be exactly the same for inverse tan.
That's what we wrote. 2n plus 1 over.
I don't think it had a
Oh,
factorial.
wait, sorry. Yeah, the factorial.
Okay, yeah. I don't think it had a factorial, but it's similar. It's similar. I like it. He was comparing to what we've done before. Other comments or questions on that? So I skipped over finding the radius of convergence for the first one and the second one. I'm going to leave that for now. I want you to try the next one and see if you can come up with a series for cosine. You may work together, you can ask me for help. Just do the same idea as what we did here and find the Maclaurin series for cosine. It's actually a little bit easier than the sine, but it's very similar, so I don't want to erase that. Erase this one. We'll come back and do this radius of convergence later. This was the first one. Everyone good what you're doing? The cosine? What happens? This was example 2. We go back and find the radius of convergence. Maybe after the break we'll do that.
This is like, this is the first.
Okay, I know some of you aren't quite done yet, and we're going to check your answers for some of you who are done. And if you still are confused, then you can ask me during the break where you got lost and whatever. But this paper I just gave you lists some of the standard Maclaurin series for common functions. A lot of them we've already done. The very first one is technically a Maclaurin series, but where did we learn that one? The 1 over 1 minus x. It's not even inverse tan.
That's the
Yeah, remember, that's the...
series of the function as a series.
Yeah, when we were writing functions in series, the section that we just did last time, right, 11.9, today's quiz that we went over, we already had learned that that's a geometric series, and we can write any series that looks in that form, 1 over 1 minus something, looks to be that in that form of a series. So that's the one we've been doing. We did e to the x earlier. We can check our work. Here's what we had for e to the x. We found that one. There it is. We didn't do natural log, but we'll come back to that one. We did sine x over here. There's that one. Looks like we were good there too. And you just finished doing cosine. It should match up to what I have written there. Did I write cosine over here? And where am I? Cosine n equals 0 to infinity. Notice they put the -1 all the way out in the front. I don't really care if you put it in the numerator, if you put it in the front, how you write that, as long as it's all there. Now the natural log of 1 plus x, we didn't do, but we could have done it in the previous section. We did something similar to that in the previous section. What would we have done before we learned Maclaurin and Taylor with that natural log function? Take the derivative, make it look like the 1 over 1 minus x form, and go from there. We also could have done the Maclaurin series steps and gotten the exact same answer.
Because that's negative.
Questions about this? This is reference, because on an exam, I'm gonna ask to actually find the Maclaurin series and do the steps to find it. But this is good reference because what we're gonna see coming up after our break is sometimes you have other functions multiplied by functions, and if you already know that we've done the work for one of them, you don't have to recreate it every time. So we'll refer to that in a minute. 1 minute after our break. Questions on that? If you still were stuck on that cosine one, you let me know during the break and I'll see if I can find where you went wrong. I think most of you, when I looked at it, were there. Okay, let's take a 10-minute break. We'll come back, we'll do a couple more Taylor and Maclaurin series and see some that are, of course, a little bit messier. All right, before we find some Taylor series, I want to go back and find the radius of convergence for that first example that I skipped over the directions. So example 1, where we found e to the x, this was our series. So I want to find the radius of convergence for that. A little review question. How do we find the radius of convergence?
Ratio test.
Either the ratio test or the root test. This one's nicer with ratio because of those factorials. So I'm going to use the ratio test. Just like we did before. No different. We're going to use the ratio test. We're going to take the limit as n goes to infinity of the n plus first term over the nth term. So I'm going to start with the n plus first term. That's x to the n plus 1 over n plus 1 factorial. That's the n plus first term. Then I want to divide it by the nth term. So that's where I'm just going to take the reciprocal and multiply of the nth term. Hopefully we've done enough ratio tests by now that looks familiar. Some of this cleans up nicely. What happens to my x's?
Just add 1x on top.
I'm just left with one more x on the top, right? All I have left is this x here, and one extra one up there. And what about those factorials? The n factorials will reduce. Remember that this means, just this one right here, is n plus 1 times the next number lower than that, which is n. And then we keep going from there, so we can actually write it this way. It's a nice shorthand way to see what's going to reduce. So the n factorials are gone. Oops, fine. So I'm now taking the limit as n goes to infinity of x over n plus 1. The x is a constant when it comes to n's. So I pull that all the way out. Absolute value of x times the limit as n goes to infinity of 1 over n plus 1. What does this expression do as n goes to infinity? Goes to 0, right? 1 over an infinitely large number. So this part goes to 0. Absolute value of x times 0 is 0. So the ratio test gave me a limit of 0. When does a series converge by the ratio test? When the limit is,
All values of x.
say that again?
All values of x.
Well, you're answering the final question, you're right. Just in general, the ratio test converges when this limit is what?
Less than 1.
When it's less than 1. And this is always less than 1. I don't care what x you plug in there. Even if you plug in 3,942,000, when you multiply by 0, it's still going to be 0. So Jose says it's going to converge for all values of x, because this is always true. Always true. For all x's. There's no restrictions on x. We don't have to force it to converge. It's already convergent. So if it works for every single x, what's my radius of convergence?
Negative infinity to infinity.
That's my interval of convergence, but the radius is just infinity. Because I can choose any number from negative infinity to infinity, which means my radius is infinity. That's my radius of convergence. We could do the same thing for the sine and the cosine. It's going to be almost identical in terms of how it reduces. They will have the same radius as well, just because of the way that they're set up. So I'm not going to do those, but you could do the same thing. You'll get infinity for both of those, because those limits will also be 0 for those two. We'll get another one coming up that has a different one, and we'll talk about it. Okay with that? We'll jog down memory lane. Okay, so let's find some Taylor series. I'm on page 157. And we want a Taylor series from 1 over x squared. This is example 3. Example 3, f of x equals 1 over x squared. And it says find the Taylor series about x equals 1, or excuse me, negative 1. That's telling you the center, centered at negative 1, about x equals negative 1. So that's telling you that a equals negative 1. Now we're doing Taylor, not Maclaurin. What's the difference? Between Taylor and Maclaurin?
Maclaurin is centered about 0.
Yeah, Maclaurin always has a center at 0, but they won't even tell you the center's at 0. They'll just know when you say Maclaurin. So instead of plugging in zeros like we did for our Maclaurin examples, we're going to be plugging in our a value, which in this case is negative 1. And instead of just x to the n, we're going to have x minus a to each power. So those are the subtle differences that we're going to have because of the center being at negative 1. The process is going to be the same though. We're going to take a bunch of derivatives, plug in our a's, see what we get. So I'm going to rewrite my function here so it looks a little bit better. This is x to the negative 2. I'm rewriting it so I can take the derivative easier. So there's my 0th derivative. What is my first derivative? Negative 2 x to the negative 3. Right, just taking derivatives. Again, this was my same warning I gave you earlier. Don't simplify when you start taking derivatives. Just leave everything written out so you can see the pattern. So when I bring down this negative 3, I'm actually going to write it like this and make it a negative 4. I know it's a 6, but to see the pattern, I want to leave it like this. You see what I did there? I'm just bringing that down. When I get to the third derivative, I'm going to bring down the negative 4. So again, I'm just going to recopy all these. I know I could simplify, but I don't want to yet. Everyone see now why I didn't want to simplify it? What do you see there? Factorials, right? I can't see, I can see factorial. I've done enough of them in my life that I recognize probably up to 6 factorial. But most of us don't recognize them. So when you leave it without simplifying, you can recognize the factorials a little bit better. Let's do one more derivative. What's the fourth derivative then going to be? It'll just be negative 5 times all that, right? So I've taken 4 derivatives. Now what do I want to do? What do I do with those derivatives? I couldn't hear you.
Write them in a sequence.
I can't write it as a series yet because I have to take each derivative and evaluate it at a. So I actually have to do some evaluating first. I need to actually get constants for those. So we've taken the derivative. So before, when we did Maclaurin, we plugged 0 into all our derivatives. Now, guess what I'm going to do? Plug negative 1 in for all my derivatives. So let's see what we get here. f of negative what? Look, this pen is dying, I had like my other one better. See, this is- What do I get when I plug negative 1 in here? Negative 1, even exponent, just positive 1, right? Because the exponent's even, so that's 1. What about when I plug negative 1 in here? This part comes out odd now, right? Negative 1 to the negative 3, that'll be a negative 1 times a negative 2. Positive 2. F of, ooh, this is such a better pen. Positive 2. What about when I plug negative 1 in here? What are you thinking, Zach? I saw you pointing.
Does it need to be written as f prime of negative 1?
Oh, yes, thank you. Thank you. Pay attention to details. What's f prime, double prime of negative 1?
Positive 6.
Positive 6, but I'm going to leave it as a factorial since we're recognizing the factorial. It is 6. Do you agree with that? Negative times a positive. It will be positive 6, but I'm going to write it as a factorial. 3 factorial. Before I go further, as soon as I recognize that this is a factorial, I like to back up and see if the ones before it were factorials as well. So this was a 3 factorial. Is this a 2 factorial?
Yes.
Yeah, it's not written that way, but it is 2 factorial, and this is a 1 factorial to follow this pattern, right? Sometimes you don't recognize the factorials till you get further down. But I like to go back and recognize that. So the third derivative, evaluated at negative 1. This will be negative because of the odd exponent. Negative times negative times negative. I got 4 negatives now, so it's positive again. And it's 4 factorial. And if I go one more, you guys see the pattern yet? Fourth derivative is going to be 5 factorial. So every single term ended up positive. And I can see I had 1, 2, 3, 4, 5, so forth. Now let me ask you a question. How do those answers compare to the derivatives? Meaning, when I took the third derivative, I got 4 factorial. When I took the fourth derivative, I got 5 factorial. What's going to happen when I get to the nth derivative? Aha, n plus 1 factorial, right? That factorial is always one more. It helps to recognize that pattern. Okay, so I have all of my derivatives. I evaluated them all at negative 1. I'm now ready to get the Taylor series. We could jump right into this notation, but I like to actually start by writing out each term to make sure we understand what it's doing. We're going to do each term. So the first term is when I take the 0th derivative, which is just f of 0. So the first term is going to have a 1 factorial on the top. That's this part. The 0 factorial here and the 0 exponent, that never changes. Technically, you don't need it for your first term, but I like to write it so we see the pattern. 0 factorial here, x minus negative 1 to the 0. That's the x minus a. Now you guys are all feverishly copying that down, but the question I have for you is, do you know where each part of that came from? And if not, ask me a question. Tell me which part you don't get. So what's the next one going to be then? Oh, someone said 2 factorial. So we started with n equals 0, so we took the 0th derivative, right? Now we're on the first derivative, which is 2 factorial. So 2 factorial. What goes down here? 1 factorial.
Times x minus negative 1.
X minus negative 1.
2 to 1.
And 1. This factorial down here and this exponent up here never change. You always start at 0, then you go to 1. I mean, technically, just when I knew it was going to be Taylor, I could have done all of this, not equal to plus. we do this part first. All of this part doesn't change. Every single Taylor series centered at -1 is gonna do this. Oops, that's a 3. 3. And then those numerators come from these answers over here. So 1 was the first 1 factorial was the first numerator, 2 factorial is the second one. Guess what the next one's gonna be? 3 factorial. The next one's 4 factorial. The next one would be the 5 factorial. So now we want to do some simplifying. Let's do some simplifying. What is 0 factorial? 1. And what's 1 factorial? So that's just 1. And x minus -1 raised to the 0? That's all just 1. I got 1 divided by 1 times 1? That's 1. Plus. What happens here? Yeah, I got 2 factorial divided by 1 factorial. What am I left with? Just 2. I'm going to simplify this too. You guys okay? X minus -1 is x plus 1? Is it 1? What happens here? What reduces?
It's the same as 3 times 2 times 1, so it's the factorials totally cancel out. Just 3 times x plus 1.
Beautiful. So the factorials totally cancel out, he says, because you want to think about this. This is 3 times 2 times 1. This is 2 times 1. So this reduces with that, and you're only left with the 3. So it's just plus 3 times x plus 1 squared. Move that out of the way because it's my way now. Similarly, what's going to happen on the next one?
4 times x plus 1 right there.
Plus 4 times x plus 1 to the cube. Let's write one more for fun. Guess what the next one is?
5 times x plus 1 to the 4th.
5 times x plus 1 to the 4th. So what do you notice about the coefficient in each case? This is when n equals 0, n equals 1, n equals 2, n equals 3. Chad's already said it over there. He said it's n plus 1. It's always one more. So this is a series. N equals 0 to infinity. I have x plus 1 to the n for sure. I have x plus 1 to the 0, x plus 1 to the 1, the 2, the 3, the 4, so forth. And the only thing I have in front here is, say it again, Chad?
X plus 1.
N plus 1,
Oh, N plus 1.
right? N plus 1. That coefficient is always one more than whichever term I have. And that is our series. Feel like there's got to be questions. The hard part again is just like we talked about a couple weeks ago. I can't show you how to recognize the pattern. You have to figure out the pattern on your own and then figure out how to write it. And sometimes writing it is a little bit of trial and error and guess and check. Write something down, plug in 0, 1, and 2 and see if it works. You'll get better at it with practice. No questions about that part? Okay, let's find the radius of convergence. Let's find the radius of convergence. This one will be different. What do I want to do? What did you say? Ratio test? We love the ratio test. It's all we do anymore. Limit as n goes to infinity. And be careful, the n plus first term, we're going to plug n plus 1 in here. So it'll be n plus 1 plus 1. Great. Okay, then it'll be n plus 2. I did that simplifying in my head. I added the 1 and this other one. Plugging in n plus 1. N plus 1. You all right with the n plus 2? Silence makes me nervous. Over the nth term. Okay? So we got this deer in the headlight look, so it's making me nervous. What happens when I go to reduce this?
X plus n, or X plus 1 to be
The x plus 1s are going to reduce. I've got an extra x plus 1 right here. These are gone, these are gone. I've got one of them left right here. So that doesn't, it's not affected by n anymore. So that's one of the ones where I pull it all the way out. Absolute value of x plus 1 times the limit as n goes to infinity of everything that's left.
equal to 1.
That limit's equal to 1, he says?
Yes.
We agree?
Yes.
Highest powers, L'Hopital's rule, whichever way you want to do it. This equals 1. If this part goes to 1, x plus 1 times 1 equals the absolute value of x plus 1. When does the ratio test converge again? When that limit is
Less than 1.
less than 1. We're going to force it to be less than 1 in this case. So this is unlike that last one we did, where the limit turned out to be 0, and we said it's always less than 1. This one isn't always less than 1. At this point, this right here is enough information to see my radius. As long as this starts with an x, if you've solved for x essentially, the radius is the number you have over here. The number is 1. If you can't tell that, you can go ahead and write the whole series, the whole interval out. X plus 1 is between -1 and 1. You don't need to get the interval because I didn't ask for it. Subtract 1 from every side and you get this. What's the distance from here, the middle? What's in the middle, number 1? -1. The distance from -1 to 0 or -1 to -2 is a radius of 1. So this number right here is your radius. Once you have just x by itself. If it was a 5x, you'd have to divide by 5, but if it's just an x, then you're good. So the radius is 1. Questions there? Check the endpoints. If I had asked for the interval of convergence, you would have to check the endpoints. But I think this one only asks for the radius. So if it had asked for the interval, we would have to check to see if this series converged at -2 or at 0. But because it didn't ask for the interval, we don't care. We all we cared about was the radius. So questions about finding that Taylor series, because the next one's the messiest one yet. So I want to make sure we answer questions about this one before we do the messiest one. No questions. Okay, here we go. Example 4. I'm erasing my formulas now. I'm hoping you stop them now. I'll read Taylor at the top. We're doing Taylor. Taylor's up there. We've got a natural log function. F of x equals ln x about x equals 2. So finding the Taylor series and finding the radius of convergence. This one's a little bit different and you'll see why. How should I start? Couldn't hear you, Joseph.
Said you should take the first derivative.
Yeah, take some derivatives. F prime of x
1 over
is
x.
1 over x. To take your next derivative, it helps to rewrite this as x to the negative 1. Just makes it that much easier to take your next derivative. So f double prime of x is negative 1 x to the negative 2. Third derivative,
-2 times -1 times x to the -3.
I love it, he's got my don't simplify thing down now. Right, he brought down the negative 2 and didn't simplify. The fourth derivative, same thing, right? Bring down the negative 3, hang on to everything else. Next to the negative 4. And let's do one more. Let's go to the fifth derivative. Negative 4, negative 2, negative, oops, I lost, negative 3, negative 2, negative 1, x to negative 5. So I took a bunch of derivatives.
Now we want to evaluate at f of 2.
Now we want to evaluate everything at 2, including f of x, which I guess maybe I'll write it over here. I can move everything over. We want to plug 2 into my every single function and derivative. What's f of 2? Natural log of 2. Okay. What's f prime of 2? 2 to the negative 1 or 1 over 2? Plugging 2 into my derivative, right? What's the second derivative? Negative 1 over 4? I'm going to leave that as 2 squared. But you're right, it's 4. Just like I like to leave my factorials, I like to leave my exponents too, and you'll see why in a little bit. What's my third derivative evaluated at 2? It's 2 on the top, and it's going to be positive, right? You guys see that? Positive 2 over 2 cubed. I know you can reduce it, but resist that urge. Because if you reduce it, you won't see the pattern. So don't reduce it until you see a pattern. I agree it reduces. What about the fourth derivative? So he's saying negative 6, but guess how I want to write it? It's negative, I agree with that. But instead of 6, I'm going to call that, yeah, so I'm going to write it as 3 factorial. Right, see the 3 times 2 times 1? It is a 6, but if we write it as a factorial, then we'll see that pattern better. So this is negative 3 factorial over 2 to the 4th, 2 to the negative 4. Some of you can simplify them and see the factorials. I'm fine with that. I mean, I can do that too, but some of us can't, so it's best to leave the factorials so you recognize them. And then finally, the fifth derivative evaluated at 2 is positive 4 factorial over 2 to the 5th. So hopefully by now we can see the pattern. There's 3 things that we should recognize in this pattern. It's alternating, that's one of them. Okay, and maybe there's a 4th thing. This guy doesn't follow any pattern, so we're going to ignore him for the moment. He's not playing nicely. But forgetting him, we create alternating, positive, negative, positive, negative, positive. So alternating is one thing we have to worry about. What's the next thing we notice? Denominators are powers of 2. This is 2 to the 1, 2 squared, 2 cubed, 2 to the 4, 2 to the 5th. And then the numerators are factorials. Let's make sure they all are. That's a 4 factorial and a 3 factorial. Is this a 2 factorial?
Yes.
Yeah, it's 2 factorial. Is this a 1 factorial?
Yes.
And what's this one? It's actually a 0 factorial, even though we didn't call it that in the first place, it does follow that pattern. I like to go back up and change them to make sure I see that it works for all of us. And the first guy is not playing nicely, we'll deal with him in a minute. Okay there? So now, I think we're ready to make our Taylor series. Here we go. Taylor series. I start with the 0th derivative, which is the original function, which in this case was ln of 2. So what was my original function? Ln x. So it's going to be ln of 2 over 0 factorial x
Plus 2.
minus 2. So it's
Minus 2,
x
sorry.
minus 8. It's okay. X minus 2 to the 0. By the way, I don't care if you skip this part, because it always goes away. But I like to write it so that you see how every term matches and everything's the same. Because these two will always be 1. So if you want to not write these two when you start off, I have no problem with that. Those will just equal to 1 over 1, which is, so they're gone. Plus, the next term, which is 0 factorial over 2. But then what do I need to do? Over 1 factorial. So instead of dividing by another one, I'm going to put the other 1 factorial down here. Over 1 factorial, so I put it in the denominator. Dividing by another 1 factorial. X minus 2 to the 1. So this part came from my derivative. This part is the 1 factorial from the formula. What's next?
1 factorial over 2 times 2 factorial.
Close, but it's negative 1. Negative 1 factorial over 2, I lost my place. Second root. 2 squared times 2 factorial. Again, this part was my derivative, that part's from the formula. You can write it as a fraction over a fraction, but it'll just get messier, and so it'll clean up nice. X minus 2 squared. Let's do one more. What's the next one? Where are we? 0, 1, 2. The third derivative.
2 factorial
2 factorial
over 2 cubed
over 2 cubed
times 3 factorial
times 3 factorial
times x minus 2 cubed.
x minus 2 cubed is all over this. And there's some more. So we've got the first 4 terms written out. So let's see if we can simplify those at all. What does this simplify to?
0.
It's not 0. What does it simplify to? Just ln of 2. Not much I can do with that. Ln of x equals ln of 2 plus, now what happens here? The 0 factorial and the 1 factorial,
1/2.
it ends up being 1/2. That's 1 and that's a 1, so this is just 1/2. 1 over 2. 1 over 2 x minus 2 to the 1. Because there are too many colors going on here. These guys reduce. The next one is a minus. What happens here? The 1 factorial and the 2 factorial.
Factorials cancel.
The factorials cancel and leaves me with,
2 cubed.
yeah, it's actually going to be 2 cubed because there's a 2 left here, there's another 2 squared here. But I'm not going to write as 2 cubed yet because we're looking for patterns. So the 2 squared was from here, and another 2, those factorials reduce and leaves me with just this 2. And it matters here because I want to point out that there's other things going on next to your 2's down in your denominator. If we put them all together, we won't see it. I agree it's 2 cubed, but 2 squared and the other 2 from reducing there. And what about here? Oh, I forgot the x minus 2, thank you. X minus 2 squared. And my next term? 2 cubed times 3, those factorials reduced again. And I have x minus 2 to the third. I think I have enough now to see the pattern. I think. Here I have a 3 as my exponent. I have a 3 being multiplied right here, and I have 2 to the third power. You see all those 3's? Now we're going to see if that matches over here. I have a 2 as my exponent, I have a 2 being multiplied, and I have 2 to the second power. So these are the things that I'm noticing. The 3, and the 3 all match up right there. Right? And over here, there's a 2, and a 2, and a 2 there. Do I have that over here?
Yeah.
I've got a 1 here. I have the 1 exponent. What am I missing?
2 to the 0?
Well, I'm missing this little,
2 to the 1.
yeah, 3 times 2. There's technically a times 1 right there. We didn't write it, but there was times 1. So that's 1 is also in there, 1 times 1. So based on that, I think I could write the next term pretty easily. Following that pattern. That's how I know if I can see the pattern, if I know what the next term is without finding it.
1 over 2 to the 4 times
1 over 2 to the 4th times 4
times x minus 2
times x minus 2 to the 4th. Because we recognize that this number, and this number are always there.
Would it be negative?
Oh, thank you, it's gotta be negative. Good job. You recognized that it was alternating too. Okay, so we have the first, 1, 2, 3, 4, we have 5 terms written down. And we want to write a general formula for it. And everybody is following this pattern except for this first guy who doesn't want to play nicely. That's fine, we'll just make him play by himself. What we do is we say this is equal to ln2 plus this other series. Forget you, if you don't want to play, we're going to throw you out. We'll add everybody else except for you. And notice this next one starts here with 1's. It doesn't start at 0, it starts at 1, because the 0th term didn't agree with us. So we'll just start at n equals 1 to infinity. And what will it look like? Forget the signs for the moment. The denominator is going to be, what does every single one of them have? 2 to the 4, 2 to the 3, 2 to the n, right? 2 to the n times n, right? 2 squared times 2, 2 cubed times 3, 2 to the 4th times 4. The numerators were all 1's. We're going to get to alternating in a minute, so I left a little space there. And then I'm going to have x minus 2 to the n. And then we just have to take care of the alternating part. Let's put that up here, maybe. -1. I usually like to do a guess and check, and I just like to start with n and see if it works. If I plug 1 in here, I'll get -1 to the 1, which is negative. Is this term negative? So that n's not correct. So how do I adjust it? Either add 1 or subtract 1, it doesn't really matter. If we make it n plus 1 though, when I plug 1 in there, it will be -1 squared. Now that is positive. And then when I plug 2 in there, it'll be -1 cubed. That will be negative. And that will help me get the alternating. So the whole thing is, I can make ln x be a series, but it has to be ln2 plus the rest of this other series. There are times you have to throw that first term, sometimes the first 2 terms out, because the pattern doesn't happen until after those. This is kind of like the ones we were doing last time where you had to integrate and solve for that plus C. You saw some of those on the last assignment. That's that plus C that you would have solved for, if we had done the old one. Questions? Yeah, then we could find the radius of convergence and our heads might explode, but we could do it. The only other thing I'll tell you is that some functions are so messy that you just can't find the pattern. And when I ask you to do, there's some problems in your lab or on your web assignment that says just find the first 4 terms, you're actually just going to do the work and simplify and write out the first 4 terms. You don't need to find a pattern, you don't need to get a formula. So if I had just said find the first 4 terms of this guy, you didn't even need to worry about the pattern. You could have just simplified each of these to see what you got. So it would have been natural log of 2 plus this reduced to 1/2 times x minus 2, right? This is the one we talked about where he's like, it's 2 cubed. So you're right, it is 2 cubed, but I didn't want to write it that way because we were looking for a pattern. But that's minus 1/8 times x minus 2 squared. I'm just simplifying each of those terms. It may or may not have a pattern. And then, which one did I leave off? This one. That's 8 times 3. 1/24 times x minus 2 cubed. So there are times, and you'll know that it's messy if I only ask for a few terms. So don't kill yourself looking for the pattern if I'm just asking for a few terms. If it's a few terms, just simplify them as you go. It's only when you have to write the whole series that I like to leave it non-simplified to look for that pattern. Okay, that's the end of Calc 2. There's nothing else to learn. Lots to remember. Lots to remember. Yes, sir.
Something the next class we have a review.
Yeah, so over there at the far left is the list of what we're doing the next 4 days. So when I see you guys on, not 4 days, 4 class meetings, when I see you guys on Tuesday, we're going to review. When next Thursday, we'll take the exam.